budem te navratio, sam ti htio reći da sam dobila pare, jel tako, pa onda zato sam ti samo to htio reći zaradi onog rada. Isto ko Karlo, pa budemo dogovorili kako bomo to isplatili i tako dalje, ne? To ide na ovo vijeće, ide, ne? Dobro, evo. Ajde, pozdrav, Bog. Okay, I think we are ready. We can start. So we stopped somewhere around here on the last lecture. So we will continue from this slide. We discussed the evaluation of quantization error. So I would like somehow to numerically evaluate or objectively evaluate what is the quality of the quantized signal. And the logical way to do it is to compute the ratio of the signal variance over quantization error variance. So I would take the ratio of these two values. So for that, in order to find this, we will use expectation operator. And this expectation operator assumes that we know the probability density function of signal as well as probability density function of the error. Starting first from the error, as we said when we discussed the quantization as a process, we understand that due to this quantization operation, I convert one segment of real values into single quantized value, let's say 0. This value is 0 value. And the error that I introduce is from -1/2 of the step size to +1/2 of the step size. That is the error introduced by taking this quantized value instead of the original real value, because the real value was on this line. That was the actual value. And by replacing this actual real value with the quantized value, I introduce this error that is -1/2 step size or +1/2 step size. And what I have to know is the distribution of this error. What is the statistical distribution? Are all of these values equally probable? Or maybe some are more probable than the others? And if the signal is relatively large compared to the step size, then in that particular case, it can be shown that this PDF, probability density function of the error, this quantization error, so this is a density of error as a function of this error value from -1/2 of the step size to +1/2 of the step size is uniform. So this density is equal to 1/delta, because the integral of the probability density function must be equal to 1. So this is equal to 1, to unity. And so I assume that all values of the error are equally probable, equally possible, from the maximum negative error, 1/2 of the step size, to the maximum positive error, +1/2 of the step size. This assumption is only approximately true. We can also show that if the signal is periodic, and if there is some rational relationship between the signal frequency and the sampling frequency, in this case, the error might not be uniformly distributed in this region. It might be discrete probability that you observe. Why? Because if I have a sinusoid as an example, and if I have only, for example, four sample values, I have only 4 sample values, I perform sampling with a sampling frequency that is 4 times the signal frequency. And the values, ideal values that I get is 0, +1, -0, -1, again 0. So these 4 values, they constitute one period of this periodic signal. But if this value is quantized, maybe for that reason, I cannot represent this value 1 but maybe only plus 0.75 as a maximum positive value if I use quantizer Q1.2 that has only 8 discrete levels, so 3-bit quantizer with 8 discrete values, plus 0.75, plus 1/2, plus 1/4, 0, minus 1/4, so on. And what I get is that this value is, in this case, truncated, or it is reduced to 0.75. And for this particular example, maximum error is even larger than this plus minus 1/2 of the step size, because the step size with this assumption was that I divide total dynamic range of the signal, this, let's say, 2 volts, and I divide it with 8 levels, because I have 4 positive and 4 negative values. And if I do so, the step size is 0.25. So this delta is equal, for this case, 1/4 of volt would be the step size. And the expected error should be plus minus delta half, and that is plus minus 0.125 volts due to rounding operation. But if I have periodic signal and period just repeat itself many times, infinitely number of times, then the error also repeats itself. Because in each of the periods, I have the same samples and they are quantized in the same way. And then the error is not random. The error is deterministic. So this value is always 0.75. This value is something else. Okay, so in this case, the distribution of the error, quantization error, is not necessarily uniform within plus minus 1/2 of the step size. But if the signal frequency is arbitrary, if it doesn't have this rational relationship to the sampling frequency, then in each of the periods of the signal, I would have different quantization errors, and really they would distribute uniformly within the range of plus minus 1/2 of the step size. The same is true if the signal is random noise. Again, if the signal is random noise, then after quantizing this signal that is noise-like, I have different quantization error for each particular sample. And in that case, the distribution of error is again uniform. So this assumption is rather optimistic assumption, I would say. So it is valid only for certain types of signal. If the signal is sinusoidal but doesn't have a rational relationship to the sampling frequency, or if the signal is maybe random-like or like some noise, again, in this case, such assumption is valid. Okay? So we will start from this because it is very easy then to compute these expectations if we have probability density function that is uniform in such a range. First, let's try to find the expected value of this E. So what is the expected value of E? And by definition, it is nothing else but the integral of E times Fe of E dE. So over the whole range of E, and the whole range of E is from minus delta 1/2 to plus delta 1/2. Okay, that is the range of the random variable. Outside this range, this Fe of E is 0. So this here is equal to 0. I don't have to consider the density out of these bounds. Okay, and now I have to find this trivial integral because this Fe of E is just a constant value. It is equal 1 over delta, 1 over delta. I can take this 1 over delta out of the integral, so I get this expected value of E, 1 over delta, and I have this integral of E dE from minus delta 1/2 to plus delta 1/2. And then, of course, we can easily find this integral, that is E squared over 2, in the range from minus delta half to plus delta half. And again, that is nothing else but 1 over delta. Then on the upper bound, it is delta squared over 4 divided by 2 minus delta squared again over 4 divided by 2. And this is cancelled. These two are cancelled because the bounds are symmetrical. And of course, we get what we already assumed, that the expected value of the error is 0. So the error goes from 0 to the left, from 0 to the right. Expected value of error is 0. But once we have found this expected value, we can easily also compute the variance of the quantization error that has such distribution. And by definition, the variance of such random signal is defined as expectation of what? Of E minus expectation of E squared. So I have to take the random variable E, I have to subtract the expected value of this random variable, take the squared value of this difference, and find the expected value of this squared difference. Okay, and again, since we have already shown that this is equal to 0, then it becomes expected value of E squared. And again, by definition, this is nothing else but E squared. So this is just copied here. Okay, times Fe of E dE. Again, in the same range, minus delta 1/2 to plus delta half. I can again extract the assumed density, that is 1 over delta. Okay, so expected value of x squared, 1 over delta. And what I have here is minus delta half to delta half, E squared dE. E squared dE. Okay? And as we know, this is nothing else but E to the power of 3 over 3 in the range of minus delta half to plus delta half. So by inserting these bounds, I get delta to the power of 3 divided by 8 minus, but again, minus minus. So plus, again, delta to the power of 3 divided by 8, altogether divided by 3. Okay, so I cancel this delta here. I put here squared, squared, squared. Okay, then I have, okay, that is delta squared. This is 1 over 8, 2 times is 1 over 4, and divided by 3. And that is then delta squared divided by 12. So we have now computed what is the expected value of E squared. So what is the variance of quantization error? The variance of the quantization error is then squared value of the step size divided by 12. Okay, now that we know how to compute the variance of the quantization error, we also have to compute the variance of the signal to have the quotient defined. And the signal is deterministic. X of n is nothing else but cosine a half. So this is the amplitude cosine of omega 0 n. This A is the dynamic range of the AD converter. So altogether is A. Altogether is A. From minus A half, if it is symmetric, to plus 1/2 of A. So we have adjusted this dynamic range such that the full amplitude plus minus A half covers the dynamic range of the AD converter. So the input gain of this signal is adjusted such that it really excites all of the codes that this AD converter can produce, from the maximum negative code up to maximum positive code. Okay. So this is this A half, 1/2 of the dynamic range of the AD converter. In the previous example, let's say that was 2 volts, for example. 2 volts from -1 to +1 volt. Okay. Now that we have this signal, how would we find the expected value of x squared? But essentially, this is not a stochastic signal. It is deterministic signal. It has a time index, so this n is simply a time index, and this omega 0 is this phase increment. So how much phase do I add for each new time sample? Let's assume that this omega 0 is 2 pi divided by 4, so it is pi over 2. In this case, as this n would go from 0, 1, 2, 3, what do I get? I get that this phase, this phi of n, is 0, p half, pi, 3 p half, 2 pi. And the values of this signal, so if it is cosine of this phi of n is what? So this is 1, this is 0, this is -1, this is again 0, and this is again +1. So I get exactly the same example that I have shown before, but in this case it is cosine signal, 1, 0, -1, 0, blah, blah, blah. If I would select some other frequency, omega 0, I would get a different sequence. Okay? So this omega 0 can be any real number. Okay, and we call it a discrete cosine frequency, omega 0. Essentially, it is phase increment. So how much phase is added for each new time sample. And if I would plot this phase function, this phi of n, as a sequence, this sequence is nothing else but a sample sawtooth wave. So I start from 0, I will get to 2 pi in 4 samples, and I have 4 equidistant samples. Okay? So this is this value p half, this is pi, this is 3 p half, and this is 2 pi, but this wrap around again to 0. So these are the instantaneous phase values. Actually, these are samples of the sawtooth wave phase function. And depending on the choice of this omega 0, so this omega 0 is this increment. How much do I add? What is the additional phase value for each new time sample n? So this here is omega 0. Okay, so now let's assume that this omega 0 is again in non-rational relationship with the sampling frequency. In this case, I wouldn't have such nice periodic behavior, so p half, p, 3 p half, so on. But if I have, for example, whatever, 1.235 pi as omega 0, in this case, I would have different samples in each of the periods. So in each of the periods, samples would be different. And if I examine what is the statistics of the phase, so what is the probability of the phase value, of the instantaneous phase value, so this phi of n. So I ask myself, if I treat this as a random variable, if this instantaneous phase value is a random variable, so what would be the distribution of this phase value? Essentially, all phase values from 0 to 2 pi are equally probable, depending on the selected omega 0 frequency. I would get different samples along this line, different samples in each of the periods. So more or less, I can say all values along the line are present in the statistics of the instantaneous phase value. So in this case, I can say, okay, this is like a random variable, but with uniform distribution. So this phi is treated as a random variable. And this density of phi is, again, uniform 1 over 2 pi. So I say, okay, the instantaneous phase value can achieve any value from 0 to 2 pi with same probability 1 over 2 pi. Again, this integral must be 1. Integral must be 1. Okay. So now that I have defined this phase as a random variable, now I can find the expected value of cosine function of this random variable. Okay, that is the next step. So this x is now function of random variable. X of phi is a function of random variable phi, and so this x of n, okay, function of phi. So x of phi, where phi is random variable with uniform distribution. Okay. Again, by definition, when you have to find the expected value of a function, in this case, let's say the function is x of phi. By definition, it is nothing else but, so expected value of x of phi is nothing else but insert this x of phi here, multiply this with density of f phi over f phi of phi, and integrate over the range of phi. And this range is from 0 to 2 pi. And we said that the density is assumed uniform, okay, uniform, and this density is 1 over 2 pi. Okay, this f phi of phi is simply constant value for all phase values, 1 over 2 pi. And the expected value then of this cosine signal is integral of this x of f, x of phi, and that is cosine phi, okay. 1 over 2 pi, because that is the density that I have extracted out of the integral, okay, in front of the integral. 1 over 2 pi. I integrate what? I integrate cosine phi, the phi, from 0 to 2 pi. And that is, of course, a high school problem. I have a cosine, and I integrate the cosine over the full period. So this is from 0 to 2 pi. And what is the integral? Of course, it is 0, because this cosine has exactly the same area, positive area, and the same negative area. The integral is 0. So the expected value of x is 0. Okay. Now that we have this expected value of x, we can also find the variance of x. Because this variance is, so this sigma x squared is expected value of x minus e of x squared. This, we have shown this equal to 0, so it becomes expected value of x squared. Okay? And this expected value of x squared, in this case, you have to remember this x is a function. So this is f of phi, and this f of phi is cosine phi. Okay? The random function is phi. This is the random function. A random variable, sorry. A random variable is phi. And then this expected value is what? By definition, again, it is nothing else but I take the integral, I take this squared value of function of a random variable, that is cosine square of phi. I multiply by f phi of phi. So I multiply by density and integrate along the whole range of this random variable, 0 to 2 pi. As before, this is equal to 1 over 2 pi, and I can extract this density in front of the integral. And I get that this sigma x squared is 1 over 2 pi integral of cosine square of phi, the phi, from 0 to 2 pi. And luckily, we can also find this integral analytically, because I can replace this cosine square with 1/2 plus 1/2 cosine double angle. So that is a trigonometric identity that this cosine square is cosine of a double angle is what? So this cosine of 2 pi is cosine cosine. It is cosine square of phi minus sinus sinus. Sinus square of phi. And this sinus is again minus 1 minus cosine square of phi. And by combining, I get the final expression that is 2 cosine square of phi minus 1. Minus 1. Minus 1. And what I want to find is, I want to find this term here. So I have to replace this cosine square of phi with cosine of double angle and a constant 1. Again, I have this 1/2 because this is 2 times cosine square. Okay, that is the way that I solve this integral. So from 0 to 2 pi, instead of this cosine square, I have 1/2 plus 1/2 of cosine of double angle 2 phi. D phi, d phi, that is. Okay. This term here is nothing else but 2 full periods of cosine. So if this double angle 2 phi is argument of cosine, what do I get? I get cosine function that starts from 0, make 1 period, make another period, and end up here. Okay, this is 1 period, second period. So this would be this 2 phi equal to 4 pi. Again, this integral, if I integrate over 2 full periods of cosine, is equal to 0. So the integral is equal to 0. That is the second term. So this second term vanishes, it is equal to 0. And what do I get? I get only the integral of the first part. And this first part is a constant, 1/2. Okay? So by writing further, so I have this sigma x squared is 1 over 2 pi. I have the integral of 1/2 d phi from 0 to 2 pi. And that is 1 over 2 pi. 1/2 upper limit minus lower limit, 2 pi minus 0. And that is, so 1/2. And then this is pi. What I have computed is the case when this cosine has unit amplitude. So I have found the variance of this cosine signal that has unit amplitude, and this variance is 1 over 2. In this example on the slide, it is the same, but this amplitude is not unit amplitude. The amplitude is E over 2. E half. Again, the variance is nothing else but the squared value of this amplitude, a squared over 4 times 1/2. So it is a squared over 8. So if I start from a half cosine of omega 0 n, that is x of n, and the variance sigma x squared is this a squared over 4 times, and we have shown that the variance of cosine is nothing else but 1/2. So we get the a squared over 8. So this is the variance of the signal that has the amplitude plus minus 1/2 of a. Now we have all that we need to find the ratio of the signal variance and the error variance. So the SQNR, this SQNR is the abbreviation of signal to quantization noise ratio. This signal to quantization noise ratio is defined as 10 times logarithm base 10 of sigma x squared over sigma e squared. So I have to take these two variances. I have to take these two variances, their ratio, and compute logarithm base 10 of this ratio multiplied by 10. This value is finally expressed in the unit that is called decibels, dB. Okay? Now we will just substitute the actual values for our particular case. But again, we will also express what? I will express this A value in terms of the resolution of the AD converter and the dynamics A. Why? Because, as we said, so this is the whole range plus minus 1/2 of A, plus A half minus 1/2 A. And this covers what? It covers 2 to the power of B levels. 2 to the power of B levels are equally distributed in this range. So if I want to compute one step size, one delta, how much it is? It is simply this A divided by 2 to the power of B, or A times 2 minus B, 2 to the power of minus B. So that is the quantization step size, delta. And if I want to express A, because I have this A in the variance of the signal, so this A, I want to get rid of this capital A. And if I just take this A from this expression, this A is then what? What? A is, so this is delta, so okay, then A is delta, this 2 to the power of B. So if I multiply the step size with the total number of quantization levels, that is 2 to the power of B, I get the dynamic range of the converter A. And now I can assume that this cosine signal really utilizes the whole range from plus minus 1/2 of the A. Otherwise, I lose some codes if I would have a lower amplitude of cosine. So this here is not effective, because in this case some codes are never used, and I lose the S to NR ratio, as we will show. So this full range of the sinusoidal signal is the best possible solution if I want to maximize the S to NR ratio. So now that I have this A, then I can use this expression to eliminate this A squared in the expression for sigma x squared. So this sigma x squared was A squared over 8. Okay? Okay, A squared over 8. And now I substitute this A, that is nothing else but 2 to the power of B times delta squared over 8. Okay? Oh, this is delta squared over 8 multiplies 2 to the power 2b. Okay? And that is sigma x. That is the denominator of the ratio. Denominator sigma e squared is variance of the error. And this variance of the error is, as we shown before, delta squared over 12. Okay, now I take this quotient, and after canceling this delta squared and delta squared, I get that this ratio, sigma x squared over sigma e squared, is 2 to the power of 2b times 3 over 2. So this is 3, it goes into the numerator, and this 8 goes into denominator, so 2 to the power of 2b, 3 half, 1.5. Okay, now I take the logarithm of this value. Okay, and so logarithm 10 multiplied by 10 of sigma x squared over sigma e squared is then 10 log 10 of this 2 to the power of 2b times 3 over 2. I can separate these two terms, the first term and the second term. The first term, so this 2b from the exponent goes in front of the logarithm. So I have 2b times 10. Altogether it is 20b. 20b. Logarithm base 10 of what? Of 2. Logarithm base 10 of 2. So this is the first term, the logarithm of the first term. And plus 10 log 10 of 3 over 2, of 1.5. Now I can actually compute what is this value, 20 times a logarithm of 2, logarithm base 10 of 2. Do you know how much this is in dB? How much this value is approximately? 6 dB, 6.02. 6.02, sorry. 6.02 times b. So this 20 times logarithm base 10 of 2 is 6.02 times b, So I just keep this b. And this is an additive term that I simply write once again, logarithm 10 times logarithm 10 of 3 over 2. Okay. We can plot this function. So this function is just a linear function. It shows that the quality increases with the number of bits. Okay, now I can plot this function. For b equal to 0, I would have this value here. Okay, so it is something that is hard to understand. It means if I don't set any information, if I simply replace the signal with a constant, what is the error, what is the quality? The quality is this log value here. So the offset of this linear term is this 10 log 10, 3 over 2. This is this value. 10 times log 10 of 3 over 2. And then for non-zero b, it linearly increases. It increases by this 6.02 dB for each bit that you add. B1, B2, B3. So for each additional bit of resolution, you gain 6.02 decibels in quality. And that is the SQNR curve, signal to quantization noise ratio, expressed in decibels. It's a linear function of rate. It's a linear function of the resolution. So if I have more bits, I have linearly higher quality. Okay. This value here, this 10 log of 3 half, is 1.76 dB. 1.76 dB. And this offset term, this offset, it depends on the signal type. It says here, this offset of this linear function model depends on the properties of the signal and its density function. It's fx of x. And for the cosine function, this offset was 1.76 decibels. Okay. Now we can also rewrite this last equation or re-examine this last equation. How does this signal to quantization noise depends on the so-called crest factor. Crest factor, and this crest factor is the ratio of the signal maximum value to signal effective value or standard deviation of the signal. So that is the square root of the variance. So this sigma x is square root of the variance. It is also called effective signal value or standard deviation of the signal. So this sigma x. And if I take the ratio of these two, I get the so-called crest factor. Crest factor says how much is the maximum value larger than the effective value. How many times is the maximum value larger than the effective value. Do you know what is this Crest factor for sinusoidal signal or cosine signal? So what is the ratio of the maximum value and the effective value for the cosine signal? And that is a question from electrical engineering. And when you say that you have the voltage, mains voltage 230 volts, so what is the maximum value of this 230 volts effective value? Huh?
Square root of 2 divided by 2.
Square root of 2, multiplied by square root of 2. So this 230 volts of mains voltage, you have to multiply this by square root of 2, and you get V max of t. So this sinusoidal signal has a maximum amplitude that is square root of 2 larger than the effective value or this standard deviation of this sinusoidal signal. So this 230 is this effective value, not the maximum value. You must be careful not to confuse. When you say you have 230 volts of mains voltage, it means it is effective value, okay? Not the maximum value. Okay, now that we understand what this Crest factor is, and we will take example, okay? The same example, okay, maybe some other example. Consider that we have some peaky signal. And this kind of signal is characteristic, this kind of behavior is characteristic for speech signal. So speech signal has very large maximum absolute value, very large maximum absolute value. But the effective value is relatively low because this peak value is obtained from time to time randomly, but not that often, seldomly. So this maximum value is obtained relatively seldomly. And the effective value is something like this. So this would be the, maybe too low in this example. This would be the effective value of this signal shown with the blue line. And the ratio between this maximum value and the effective value, so this A max over A effective, is this Crest factor delta. Okay, and now we will use this Crest factor in order to define the required dynamic range of the converter, but expressed in terms of the effective value of the signal. So now I will say this signal has the effective value sigma x, okay? And what is then the maximum value? The maximum value is simply this sigma x multiplied by the Crest factor delta, okay? So signal max value is plus minus delta times sigma x. And I have to accommodate with the dynamic range of the converter to cover the whole range of this maximum signal value. So this must be equal to plus minus a half of the AD converter. So this delta times sigma x must be contained within plus minus 1/2 of A. I don't want to clip this value. So this is then equal to plus 1/2, and this here is minus 1/2. Why? Because I don't want to clip this value to have saturation. And then, since I have this expression, this sigma A, okay, A is then what? A is from this expression what? 2 times delta times sigma x. So the dynamic range of the converter must be equal to 2 times Crest factor times the effective value of the signal. Now I will use such A in order to find the step size, the required step size that I have in denominator for the variance of the quantization error. So the step size in this case is nothing else but this A divided with the total number of levels. So this A was 2 times delta x, 2 times delta sigma x, divided by 2 over 2 to the power of B. And I use this delta in the denominator for the S squared R ratio. S squared R is then 10 log 10 sigma x squared. I just write sigma x squared, and this here should be sigma e squared. And sigma e squared is, as we said before, delta squared over 12. The step size, squared value of the step size, divided by 12. And I take this delta from this expression, I put it here, and then I put this sigma e squared here. And of course, this sigma x squared is cancelled. It is in the numerator and in the denominator of this ratio. And I get the expression in terms of delta and B, of course, because this B is still present here. In terms of B and in terms of delta. So this S squared R, at the end, it becomes S squared R is blah, blah, blah. So I still have this 10 log 10 of 2 to the power of 2b. And the second term, that is 10 log 10 of 3 over delta squared. So this crest factor is in the second term, it defines the offset of this linear function. So the first part is the same as before. So this is nothing else but 20 times b times log 10 of 2. So rewritten, it is 6.02 times b, this here. And the second part is dependent on the crest factor of the signal. And now we can easily check whether we got the right result, because with the sinusoidal or cosine signal, so for sin or cos, this delta was square root of 2. And if I put this square root of 2 in this denominator, 3 over delta squared, I get exactly the same expression that I had before derived for the sinusoidal signal. So this 1.76 dB is the solution when you have this crest factor of square root of 2. But for the example of speech signal, where this crest factor is much larger, maybe 5, 10, okay, then this second term is actually negative. So this offset of this function becomes negative. Why? Because if this value is less than 1, then the logarithm is negative. So if this, the limit case would be delta square equal to 3, then the offset is 0. But if delta square is larger than 3, then the offset is negative. And it shows that the quality of the quantization depends on the crest factor of the signal. Larger the crest factor, lower the quality of the quantization. Okay, so more or less that concludes the first part of the lecture. Now we have break. Do you have any questions regarding this part? More or less it was a rather simple mathematics, I would say. High school mathematics, maybe not high school, but first grade university mathematics. Okay? So 15 minutes break. I will store these contents of this electronic blackboard or whiteboard such that I can share it with you later on.
Croatian?
Yes, yes. Where are you from?
Spain.
Really?
Yeah.
Oh, that's so nice.
Thank you. Oh god. I'm a little bit worried about this lecture because I think that it's going to be
I actually, this is my second time listening to this subject. I had some private issues, so I didn't get to go to the exam last year. Annoying. But
as you see,
it's not difficult. It's just like really boring the first part, and the materials aren't really welcoming, but the second part is way easier. Which subjects are you listening this year?
I have communication networks, local area networks, multimedia systems, and technology in medicine. I have like 4.
I have 4 too. This semester, but only this one we're listening together. So, how long are you here?
I've been staying here from September. Like I've been here for the whole year.
Oh, really?
Yeah. So it's like my second semester here.
Are you a student home or?
I'm on a residence. Wait, I'm going to try to pronounce it. It's Viendo en Australia? No. Yeah.
It's okay.
Okay. I've been practicing for the whole month, like trying to get it right.
Well, do people already teach you cursive or only nice words?
Nice words. Well, some I know a little bit of words, but that's all. Yeah, I don't know what Croatian actually is.
Oh no.
It's difficult.
I'm sure that I'm sure you get it better. So. That's okay.
Also, it's like 3 hours now. Here in Croatia you have like a lot of hours now, but in Spain we have maybe like 1 hour or 2 hours, and then like another day, another 2 hours.
Well,
It's different.
when I was in my first year, my schedule was like from Monday to Friday, from 12 p.m. a.m. like the middle of the day
Yeah.
to 6 p.m. and I was like,
God, really.
I hated my first year. Yeah, now I'm watching a movie on Netflix by
The problem for me is that like the slides are in Croatian, and the professor told us that he was gonna like update them like on English. And I'm still waiting for it because it's like I don't understand it, and it's difficult for me. Like I understand English totally, but it's difficult for me to take notes while he's like saying something.
Yeah,
Because I like lost the track of what he's saying sometimes. But I mean, if you say it's just boring and it's then easy, I trust.
I remember it's like 3 parts of the class, and the second part, I remember we were teaching about TVs and stuff, like the resolution,
Yeah, with
like
like
the picture. Yeah, I really like that part. And the third part is like, it's complicated stuff, so we will go with basics, so then it's easy. And this is like just math.
Yeah, but like in the at least in the midterm exam, like you have like some exercises practice, right?
Well, the midterm should be like when we have our laboratory exercises and homeworks. We have like 11 tasks for homework, and the test should be similar to that. Like that's your exercise.
Well, that's good. And like the homework and the laboratories difficult or
I did them online because lockdown and stuff, but I think it shouldn't be actually any different in person. You just like copy stuff and it with MATLAB. Click.
Oh, MATLAB. Okay. MATLAB.
But like you get most of the stuff written, you just try it out. I've been using that program for like 3 years and
Yeah, I've been using it just like for one semester, just because last year I had in Spain like I think that it was signals and systems, like the course that I was taking, and we had to use MATLAB and it was like a mess. Because like they didn't teach us exactly how to use it. So like I know how to use it just because I'm trying to learn from by myself. So I hope it's okay.
like literally everything I don't know, I just type it into YouTube and wait for something to get it out to and wait to me.
Just have to go upstairs somewhere and then to get it. I don't know.
That's interesting.
No, but I didn't do like about the activities.
A lot of things to do.
Yeah.
Everything is closed.
Yeah, it's
Okay. Nice having you as well.
papira. Što nećete koristiti, možete moje papira staviti u opic. Hvala papir samo. Okay. So, going further, I have started the example during the break time. This example tries to illustrate how this quantization really works on actual signal, on example of sinusoidal signal. And I will try to explain this MATLAB code that demonstrates the quantization operation. The MATLAB code is relatively simple and short. It is included in the materials for the first lecture. You can find this example. It is called MT01 MT01 quantization. If I activate this demo mode, it will go signal by signal. As an example, it will quantize this signal. It will reproduce on the speaker the original version and the quantized version, such that you can hear the difference caused by quantization. And it will also visualize this waveform on the plot. I will start maybe the example, then I will discuss the details of the code. So if I just press enter, the plots are the following. Okay, so this here is the original signal with some randomly chosen frequency. This W is like omega, so this omega is this omega 0 that multiplies n. So omega 0 times n is the instantaneous phase. And this value of omega 0 is randomly chosen. In this example that you just heard, it is 0.9575, okay, radians. And with such a sampling, the continuous wave is shown with a blue solid line. The continuous wave is sampled with these green samples. These round green symbols, these are the sample positions if I select the sampling frequency of 8 kilohertz. So in this example, the sampling frequency is chosen at 8 kilohertz. And the signal frequency is this omega 0. So I want to compute what this signal frequency is actually in hertz. If I want to find the hertz frequency, thank you, then what I have to do, thank you, then I simply have to divide this omega 0 with 2 pi and multiply by sampling frequency. And that would be signal frequency in hertz. So this randomly chosen discrete signal frequency omega 0, in the example shown here, 0.9575, I divide by 2 pi, so 6 point something, and multiply by the sampling frequency. In this example, I have chosen the sampling frequency of 8 kilohertz. And that is the frequency of the sound that I have just heard. Okay? And the samples are these here. So within one period, this will be one period, I have how many samples? 1, 2, 3, 4, 5, 6, 7 and a half. Approximately 7.5 samples. This 7.5 is actually this ratio here. So number of samples per period is this 2 pi divided by the phase increment, omega 0. And in this case, this 2 pi is 6 times something, 6.28, blah, blah, divided by this value that is approximately 1, slightly less than 1. So I get exactly this 7 samples, or 7.5, as I can observe here. 1 sample, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 6.5. Okay, 6.5 samples per period would be approximately for this example. No, okay, so these green points are ideal real numbers. So they are not quantized yet. And I will now try to quantize these values with how many bits? I have to check. I think it is 3 bits. So I have only 8 values, 4 positive values and 4 negative values that I would quantize this signal. And after quantization, if I just press space, not here, but I have to press space here. So it shows with this light green curve, it shows the quantized value of this ideal value here. So this does not have fractional representation with 8-bit integer, no, 3-bit integer, sorry, 3-bit integer. And the closest value that you have with this Q1.2 representation, Q1.2, is this value of minus 0.75. This here, this step here corresponds to this minus 0.75. Okay, this here corresponds to minus 1. This here is minus 1/2. Okay, the upper value is plus 1/2. This value here is plus 1/2. This value here is plus 1/4, 1/4. Okay, so these horizontal lines, they show how this quantized signal looks like after I quantize the ideal real value with only 3 bits. So 1 sign bit and 2 fractional bits for the value. So for this example, I use only these 8 possible values. 0.75, 0.5, 0.25, 0, minus 0.25, minus 0.5, minus 0.75, and minus 1. So I take the closest value of the real signal, this green dot, to one of those 8 values that are quantized output of the 3-bit converter. You can observe still here that I use this value. I have added this value that normally does not exist in the representation, in 3-bit representation. I have added this value plus 1 just for symmetry to avoid this clipping that I don't have on the negative side. On the negative side, I go to minus 1, but on the positive side, I don't have this code 4. I have code minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3. But in 2's complement, normally you don't have this value 4. But for symmetry reason, I have chosen to add this last value additionally to this range. So I have plus minus 4 representation, although I declare it as a 3-bit quantizer. Okay? Okay, so this is the quantized value. So now I have to reconstruct the original signal from these quantized values. So from these horizontal lines. This horizontal line, they represent the integer value from minus 4 to plus 4. I want to restore the original signal. And I do it by interpolating this ideal interpolation function, sinc function, through the green samples, not dark green round points, but to these corners. So I take these corner values, this quantized value, and I interpolate through this corner quantized value this ideal interpolation function, sinc function. Okay? And what I get by adding all these sinc functions that are infinitely long, in the actual implementation they are finitely long. So I have chosen certain width of this sinc function to the left and to the right that approximates this infinite sinc function. And if I add up all this sinc function for contribution of each of the quantized sample, I get this red curve. So this red line is the reconstructed signal from the quantized samples. Okay? Maybe another example. Okay, maybe here. So very low frequency signal. now I have many samples in one signal period, and now I can see this quantized value, so 0, 1, 2, 3, and 4. 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. Okay, so these are the quantized value, and I interpolate through the corners of this curve, this light green curve. So this is here a sample, this here a sample, this here a sample. I interpolate this ideal interpolation function, this sinc function. And by adding this contribution of each individual sample, I get the red curve. And this red curve approximates the original blue continuous wave. So the difference between the original sinusoidal wave and this red, quantized, reconstructed sinusoidal wave is the error. And the plot here shows what is the histogram. So what would be this is the approximate estimation of the probability density of the error. So this error must be plus minus 1/2 of the step size. In this case, the step size is 1/2 is the total range, so plus minus 1/2 is the dynamic range. And I have 4 values, positive, 4 negative, so the step size is 0.125, so 1/8. The step size in this example, delta is equal to 1/8, so 0.125. And the expected PDF of the quantization error is from 1/2 of the step size minus 2 plus 1/2 of the step size. And this is this value that is shown here. So 0.06 blah, 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 that is 1/2 of the 0.125. Okay? And what we have expected is to see equal distribution of each possible error values in this range. But we do not observe ideally equal distribution. But for some reason, the values around 0 are more probable than the values closer to plus minus delta half. So this is the empirical distribution of the quantization error for this example. So I simply compute the ideal value, I compute the quantized value, I take the difference, and I compute the statistics of this difference. So how many times do I get the value in this bin, how many times in this bin? So this histogram is the approximation of the actual PDF, but that is based on uniform bins. So uniform equidistant regions for all of possible values of the error from the maximum negative error to the maximum positive error. So now I go on further. Another example. Okay, but now you can really hear the difference. I play the original sinusoidal wave and I play the quantized sinusoidal wave, reconstructed wave. And you can hear that these two waves, these two signals are not the same. But they are still quite close. So if I simply put the volume up to be able to hear this subtle difference between the original and the quantized signal, you can hear this distortion. That this ideal signal, you have some kind of added distortion, and this added distortion is this difference between the blue and the red curve. So the reconstructed, interpolated signal from the quantized sample is quite close to the original continuous unquantized signal. And really we can hardly distinguish the original and the quantized signal. Maybe it is easier to distinguish the difference for low frequency signals, where this distortion is as some kind of additive signal that is added to this slow signal. So I have low frequency signal with some additive high frequency contribution, and I can easily distinguish the original signal from the quantized. But this is only 8 levels, so to be more precise, 9 levels. So from 4 to -4. I represent the original signal with only 9 discrete levels. And even with such crude quantization, it's very hard to distinguish the original from the quantized version. If I simply add more bits to the quantizer, so if I terminate this execution, Control C, and if I change the resolution, so this B here, B, okay, I somehow changed here. So this B is, for example, 6 bits. Now I save it, and I run it. Now you can see that these red and blue curves are almost identical visually. And the sounds, they really are almost indistinguishable from each other. Okay? And that is with only 6 bits, if I remember correctly, 6 bits. And what do you have as a nominal quantization resolution for high quality audio or for CD quality audio? The signal is quantized with 16 bits, not 6, but 16. So with 6, you cannot hear the difference. But with the CD quality representation, each sample is represented as a 16-bit integer. So you have from minus 32,000 something to plus 32,000. These are the output integer values of the AD converter. Of course, I can put here these 16 bits as an example, and you will see that really there isn't any difference between the original and the quantized version of the signal. Obviously, it must be so because since even at 6 bits, I could not distinguish. With 16 bits, it is even more so. And now this probability density function is closer to this ideal uniform distribution. So this assumption of uniform distribution is more valid if I have high resolution. Okay? If I have very crude resolution, 3 bits, then this assumption is approximately true. Okay, so you can play here with the frequency. You can select, but just to show this rational relationship between the frequency of the signal and the sampling frequency, now I will force the frequency omega 0 to be, for example, this here. Instead of having a random frequency, omega, I will select that this omega is p over 8. So I would have exactly 16 samples in one period of the signal. But in each period, exactly the same 16 samples will be present. Okay? So if I run this code, but with this fixed frequency of the signal, so I can count these 16 samples. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have exactly 16 samples within one period. But they are the same 16 samples, and the probability density function of the error is discrete. Because the error is also discrete. Only certain values of error are possible, since only certain values of signal are possible. So I'll repeat 8 different signal values, 8 different quantized values, and then I have this 8 unique errors. I have 8 unique errors, and this PDF of error is then discrete. Okay? It is always the same signal, okay? And this PDF is discrete. Okay, I think it exhausts this example. You can play on your own with this empty 0, 1 point underscore quant. And there's one more thing I want to show, and that is, instead of playing one signal at a time for a chosen bit rate, for a chosen number of bits for the AD quantizer, I will try to quantize the same signal but with different resolutions. And that will be done here if I just take this demo to 0, demo mode to 0. In this case, it will run the quantization from 1 bit to 16 bits per sample. And compute what? It will compute exactly what we have derived on the whiteboard. It will compute the SQNR. So what is the signal to quantization noise ratio, but empirically. So to find what is the variance, so the average squared error. What is the average squared value of the signal? And take these two in the quotient. Okay, and I will get the empirical signal to quantization noise ratio for all of these rates from 1 to 16. So I run this code. I cannot right now explain what happens here, but more or less you should observe that this empirical SQNR follows this ideal linear model. Okay, so this line here is the derived linear model, this SQNR as a function of number of bits. So this 6.02 decibels per bit with the offset depending on the chosen signal. This offset in this case is this 0.176 dB, since this signal is sinusoidal. What happens for 10 up to 14, I don't know, to be honest. It is something erroneous. It should not behave like that. Okay, I have to check this because each year I change slightly this code, and I'm never certain that really it performs correctly. Okay, so normally it should be these blue dots should follow this line for all of this resolution up to 16 bits. Okay, and now I will go back to the presentation. Okay. So these last few slides describe the example that I have shown in MATLAB. It describes parts of the MATLAB code just shortly. So defining the sampling rate, defining the number of samples that I will use to demonstrate. It is 4,000 samples, so it is 1/2 of the second that I use for the synthetic signal that I generate. This is the sequence of time indices, and this is the dynamics of the AD converter, so plus minus 1/2, so A is 1. I take the random frequency and I construct a sequence of values, A half times cosine of this random frequency omega times this sequence of numbers 0, 1, 2, blah, blah, up to n minus 1. And then I select the number of bits for the quantizer, and based on the chosen resolution, I compute the step size. This D, capital D, is the quantization step size. How do I compute it? I simply take the dynamics, so this plus minus A half, this is the total dynamic range of the converter, and I divide this range with the number of levels. And this number of quantization levels is 2 to the power of B. So in the example shown before, with B equal to 3, that would be 8. So I simply divide this A with 8. Now that I have this step size, I perform the quantization by dividing the ideal real value with the step size, rounding this to the nearest integer, and after that I simply again multiply with the step size. And I get the quantized value of the signal with the chosen step size, capital D. once I have this quantized signal, I can compute the error. So the error is simply the difference of the original signal and the quantized signal. And now I use the sample mean to approximate this variance estimate. Okay, this is just a mean value of the squared error. So I assume that the mean value of the error is 0. I ignore this, and simply I can find this expected value of the squared error as the mean value of all of these error samples for all capital N samples. And the same here is the energy of the signal. It is the mean squared value of all signal samples. And if I take these two into ratio, 10 log 10, I get the empirical signal-to-noise ratio for chosen B. I store this value, and finally, I compute the model. The model should be 20 times number of bits. This is a vector. BB is a vector 1 to up to 16. Okay, so this is the linear part of the model, and this is this offset of the model, 10 log 10, 2 over 3 for the cosine signal. Okay. And these are these plots that I have shown in a real execution. Okay. This is for 8 bits, and the first example was for 4 bits. First example was for 4-bit quantization. Okay. And this is the one that you should find at the end. So why I have this strange behavior, I will have to examine during the break time and find the reason for this strange behavior at high resolution. Okay, so more or less, finally, discussion. So this model shows that it predicts the behavior of the quantizer quite accurately. The expected value of the SQNR is followed by the actual empirical SQNR closely. You maybe have some deviation from the model, but only for very low resolution. So you expect that this model is really highly accurate for high bit rate. So for high resolution, the actual empirical SQNR should very closely follow the model that is based on this linear curve. The deviation from the model might occur only for very low resolution of the quantizer. Okay? Then it says the same here in Croatian. And as we have observed, the histogram of the quantization error is closer to the assumed uniform distribution as soon as we select higher resolution. When we selected a low resolution, like 3 bits, then this distribution had some peak in the middle around 0 error. But as soon as we select higher resolution, like 8-bit or 10-bit, then it is closer to this assumed uniform distribution. So blah, blah, blah. And this fact that this model predicts the behavior at higher resolution more accurately is the basis for the so-called high-rate quantization theory. So this high-rate quantization theory is exactly based on this assumption. Such statistical models are very close to the empirical solution or to the empirical case if the rate is sufficiently high. And for that case, we will show that the behavior of the system can be characterized rather simply based on these theoretical derivations. Okay? This covers what we have covered so far. Okay, this slide just summarizes what we have covered so far. Now I will go on with the second part of the presentation, and that is what is the so-called raw signal. So what is the raw media signal format? In Croatian format nominalne točnosti, raw media signal format. So what we are interested mainly is what is the data rate, what is the media stream data rate. And this data rate, this raw data rate, is defined what? By the sampling frequency and by the resolution of each individual sample that I quantize. Okay, this data rate R is simply number of bits or bytes per second of media signal or per one media object, depending whether it is speech, audio, image, frame, whatever. If I have one-dimensional signals, then this data rate is simply a product of resolution of the AD converter, this B, multiplied by the sampling rate. So Fs is the sampling rate in hertz. So if I have 8 kilohertz, and if I take 3 bits, then 3 times 8, it is 24,000 bits per second. So for this very crude example, with only 8 quantization levels, I would have the rate of 24 kilobits per second to represent such a signal with only 3 bits per sample. So that is trivial. With your CD quality audio, this sampling frequency, it has some standards. One such standard is CD quality audio. So this sampling frequency is 44.1 kilohertz. Why 0.1, nobody knows. Maybe they try to avoid some subharmonics of mains for that reason. So they have not chosen 44 kilohertz. Another often chosen sampling frequency is 48 kilohertz. So 48 kilohertz. And they also have now multiples of this sampling frequency. Nowadays, AD converters can operate at twice this value. Okay, so 2 times Fs, it is 96 kilohertz. But even if I multiply this value by 2, I get 180, what? 192. 4 times sampling frequency, 192 kilohertz. It is really very high frequency, and you can find AD and DA converters for the audio applications that really support this sampling frequency. Not for joke, but for actual. So they really support this frequency of 192 kilohertz sampling rate. When they started from this CD quality, it was this rate here, 44.9 kilohertz, and they had 16 samples, 16 bits per sample, 16 bits per sample. But they have 2 channels. Why? Because they have left and right channel. So you have stereo signal that needs 2 channels, left and right, and I have 16-bit samples for the left channel and 16-bit sample for the right channel. Altogether, 32 bits. And if I multiply all of this together, 44.1 times 16 times 2, I will get approximately 1.5 megabits. 1.5 megabits. That was the raw data rate for the CD quality audio. And when you bought first of such CD players, what this laser was reading from the disk was exactly this rate, 1.5 megabits per second, 010101, and it was converted through DA converter to the analog signal that had this 16-bit accuracy. For the left channel, 16-bit accuracy for the right channel. As we have shown in this example, it is more or less an overkill. Because with 6 bits, it is almost indistinguishable. With 16 bits, it is really absolute overkill. Okay, but for nowadays, AD and DA converters that are used in audio applications, they have increased this resolution from 16 bits to 24 bits per sample. So they have added 8 additional bits in resolution. And they have increased the sampling frequency from this 44.1 up to maybe 192 kilohertz sampling rate. Okay, so obviously this is the increase of 1.5 times regarding the resolution, and this is the increase of 4 times regarding the sampling frequency. So altogether it is 6 times higher data rate compared to the original CD quality audio. Okay, and the next question is, so what is the bandwidth of such signal? So what is the highest frequency that you can generate with such DA converter that operates with 192 kilohertz sampling frequency? Theoretically, 96 kilohertz. Theoretically, you could generate at the output of DA converter sinusoidal signal that is of frequency 96 kilohertz frequency, output frequency. As we have discussed on the previous lectures, this part of the operation is not possible due to the interpolation limitation. And this last from 0.9 to 1 of the half of the sampling frequency is part where you have this problem with the interpolation. But the highest frequency you can expect is practically 1/2 of the sampling rate times 0.9, approximately. So 90% of the 1/2 of the sampling rate. With such frequency, you can still have almost ideal sinusoidal output at the output of DA converter. Okay? So the maximum frequency of the output signal, if you use sigma delta converters, and that is this special type of implementation of DA and AD converter. With such a converter, this maximum frequency is approximately fs half multiplied by approximately 0.9 or 0.95, depending on what quality do you require. So if you require really very high quality, then it is 0.9. If you are satisfied with slight degradation, then you can also go into this range up to this last 5% of the band. So shown here, so this is this Nyquist frequency, fs over 2, this is 0. You cannot operate in this last 10% of the band. In this part of the band, you have the interpolation problems with the actual DA converter, but more or less up to this point it works perfectly. And for this example, if I have 192 sampling frequency kilohertz, this frequency is, let's say, 90 kilohertz, 85 kilohertz, somewhere around that range. Can you hear such signal that has a frequency of 85 or 90 kilohertz? Definitely no. So when you are young, the highest possible frequency that you can hear is maybe 16 kilohertz. Okay, so for a young person, F max is approximately 16 kilohertz. And when they claim they can actually reproduce frequency that is 90 kilohertz. Okay, so it is 6 times or 5 times larger than the highest frequency you can hear. It is more or less just a commercial bullshit. It doesn't have any practical implication for the human listener. Who can really hear this part of the spectrum? Only bats. So these bats that fly around hunting for mosquitoes, okay, they can hear this part of the spectrum, but not humans. So if you put the reproduction of your high-quality audio, and if it really supports this part of the spectrum, so not only the output of the DA converter, but the whole chain, and that is the power amplifier, the speakers, and the driver on the speaker. So on this speaker, there is a very small driver for the high-frequency range of the audio bandwidth, okay? And this high-frequency driver must support such output frequency. Usually it does not. So maybe it has a cutoff frequency at around 20, 30 kilohertz, and that's it. So you cannot reproduce. Otherwise, if we want to reproduce this range above 20-something kilohertz, you must have special transducer, Piezo Transducer. So it is used in ultrasound. So if you have to emit the ultrasound, you must use a special transducer that is suited for ultrasound generation or reproduction. It is usually based on piezo effect, okay? But normal speakers, they do not support such high frequency. So essentially, this part of the band, it is just for commercial purposes. You cannot hear it, you cannot reproduce it with the normal speakers. The normal power amplifier does not pass it through, it just cuts it out. So whether you have it or not on the output of the DA converter, it doesn't make a difference, okay? Going further, for the images, I have the spatial resolution. This spatial resolution is the number of horizontal and vertical pixels, so columns and rows. How many columns do I have in the image? How many rows do I have in the image? So M times N, capital M times capital N. And if I want to compute what is the data rate for one still image, I simply have to multiply the number of columns times number of rows and times number of bits per pixel. For the image, typically you have 8 bits at most for one pixel. Maybe 10 bits, okay, and that's it. So, because otherwise we really cannot distinguish the value that is 10 bits. So for us, it is all the same gray value if you change the last significant bit. So for that reason, for the image, typically this B value is 8, maybe up to at most 10 bits per pixel. And that is if the image is monochromatic, so if it is only gray and white. Okay, black and white with gray levels, okay? But if the image is if the image has RGB colors, then I have to multiply this value by the number of channels. Okay, so if I have 3 channels, red, green, and blue, then the data rate is not only B times M times N, but also times 3 because I have 3 values for each pixel. Finally, if this is not a still image, but a video sequence, then this happens how many times? It happens depending on the frame rate. So this this FR is the frame rate. So I have to multiply this value, number of bits per pixel, resolution of the image, times frame rate, and I will get how many bits do I have per second for one raw video format, okay? Again, if I have RGB image, so 3 channels, I also have to multiply this value by 3 to have the raw data rate for video signal with RGB representation. It is discussed here. So multi-channel for audio is left to right, minimum stereo, okay, if it is not mono. But also you have this spatial audio, this 6-channel audio, 5.1 or 7.1, blah, blah, blah. So you have these additional channels that tries to reproduce the spatial characteristics of the audio signal. That you are, like you are sitting in the middle of Carnegie Hall, you have exactly the same acoustic environment that is synthetically created using set of spigots. Okay, and so instead of having only 2 channels, I have 6 channels or 8 channels. Okay, but for the images or for video, then this multi-channel is actually number of primary colors I use to represent each pixel, and typically it is 3 primary colors: red, green, and blue. But that is only one possible representation for the color image. And Professor Grgić, Sonja, she will learn you all other different representation of color image space. Okay? And this here we have just discussed. Now we have 4 minutes behind the schedule. Okay, we have discussed that all of this, it must have some meaning in the concept of our perception. So it's not meaningful to add just another bit just to have a commercial advantage in comparison to your competitors, but it must have some really useful meaning for the listener. And nowadays they have already achieved this limit. So it does not make sense to increase either the resolution or to increase the rate, because the perceptual limits are already achieved. Okay? Also, what is necessary to understand, you have significant contribution of the noise signal, okay, in the actual system. So all of this ideal stuff is more or less bullshit if you do not consider noise. And where this noise comes from? From the actual system, from the actual implementation. This power amplifier, it is not noiseless power amplifier. So it amplifies your signal, useful signal, but it adds a noise to this signal. So it also amplifies a noise. So although your input to the power amplifier is ideal, almost ideal, with the amplitude resolution as is nowadays 24 bits amplitude resolution. Okay, 24 bits per sample. This is incredible. This 24 bits, how much is this? It is it's 16 bits. I would have the range, okay, so plus minus 1 volt. I divide it with 2 to the power of 15. So with 16-bit representation. So this LSB value is actually 1 over 2 to the power of 15. So 1 over 32,000 plus 768. Okay? And if I add 8 bits more, I have to multiply this value times 256. Okay? So this is for the 24-bit representation. So what do I get? So this is approximately 3 times 10 to the power of 4 times, and this is approximately 3 times 10 power of 2. I get 9 times 10 power of 6. So this is approximately 10 to the power of 7 in the denominator. So how much is that? It is 0.1 microvolt. So if this 1 in the numerator is 1 volt, this 1 volt is divided by 10 to the power of 7. And what you get is this delta level is 0.1 microvolt if the input range is plus minus 1 volt. Do you really expect such a small noise in the actual system? Never. Never. So if you want to have a system that has approximately 60 dB signal to noise, it means 1 to 1,000. So the signal to noise is 1,000 ratio. So the effective value of the signal is 1,000 higher, larger than the effective value of noise. So this 16 dB noise level, it means 1 over 1,000 ratio. And this here is how much? It is insane. So this is this value 10 to the power of 7. This is 140 decibels. You take this exponent, okay, and multiply this exponent by 20 to get the dB value. So what you are requiring that your system must be designed to 140 dB quality signal to noise. If you have done any electronics in your life, then you know that to achieve 60 dB, you have to work a lot. So you have to take great consideration for noise sources, for shielding, virtual zero shield, blah, blah, blah. But to achieve 140 dB is practically impossible. So for that reason, the output of the AD converter, or DA converter, let's say, only the upper part of the word is relevant. The lower part of the word is more or less completely random. Okay, so to have this kind of 140 dB quality, not with the AD or DA converter, but with the rest of the system, is practically impossible. So that is the reason why 24-bit resolution for the AD or DA converter does not make much sense, because all of other systems that are connected to AD or DA are of much lower quality than the converters, okay? And it is discussed here. So 24-bit resolution, this one step size is only 0.1 microvolts large. And all different contributions of noise, thermic noise, or electronic noise, or crosstalk, all different contributions are much larger, several orders of magnitude larger than this 0.1 microvolts. Okay? And this here discusses the problem of sampling frequency, that it also does not make sense, because a young and healthy person can hear up to most 16 kilohertz signal frequency, while this output of the DA converter goes maybe up to 77 kilohertz or 80 kilohertz. So this whole range from 16 up to 80 is practically unhearable. Okay? They say you cannot hear it with your ears, but you can hear it maybe with your guts. So in your belly, you can hear this very high frequency. That is the theory. So they say you cannot hear it with your ears, with your brain, but maybe with your belly, you can measure these very high vibrations. Okay? Theoretically. Okay. Blah, blah, blah. So just as an example, the typically highest rate that you would observe in an engineering situation is where it is connection between your PC and your digital monitor. So your digital LCD screen that has, for example, 8K or 4K resolution. Try to compute what is the data rate between your computer and your high resolution screen. In this example, it shows only full HD resolution. So 1920 for the horizontal resolution, 1080 for the vertical resolution. And that is approximately 2 megapixels. So I have 2 million pixels for one HD frame. I have 3 channels, R, G, and B. And if I select, for example, 8 bits per channel, or even 10 bits as an alternative for high quality, okay, and if I select the frame rate of only 16 frames per second, few of you that play games, video games, prefer 120 frames per second to have smooth motion on your screen to avoid these flickering effects. Okay, but if you have only 16 frames per second, so you simply multiply this 3 times blah 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 times 8 times 60. What you get is 3 gigabits per second, 3 gigabits per second, with a simple HD resolution, okay? With only 60 frames per second. If you use 10-bit representation for the amplitude, for each RGB value, and then it is increased to 3.7 gigabits per second. But nowadays, what you have, you don't have full HD. You have this 4K or 8K. And that means with 4K, it is twice that in both directions. So it is altogether, instead of 2 megapixels, it is 8 megapixels one frame. So with 4K monitors, you get twice the resolution horizontal, twice the resolution vertical, altogether 4 times higher resolution compared to the full HD. So this rate is simply multiplied by 4. Instead of having 3 gigabits, I have 12 gigabits to send information from your PC to 4K monitor. Okay? And all of this is done serially. So the connection is serial connection between the output connector of your PC, video card, and the input of your monitor. The transmission is serial. It is not done over a single lane, over a single twisted pair. It is done over several such lanes. They are combined just to aggregate the total rate to achieve this 12 gigabits per second that you need. Because through one lane, through one channel, you cannot transmit more than maybe up to 10 gigabits per second. Okay, 10 gigabits per second is the highest possible frequency data rate you can transmit through a single twisted pair wire. Not more than that. Okay, and you can find all of this in the specification of the new HDMI standards. So if you write into Google HDMI, you will find the newest HDMI standard that supports the highest possible frame rates, highest possible resolution that your PC and monitor can operate with each other. Okay, and that is the practically highest possible media data rate you will observe in your engineering environment. For with audio rate, with anything else, it is much, of course, much less. Okay, so it is now 6:15, so we will make maybe 10 minutes break, and then we will end up 10 minutes earlier. Okay? 5 minutes earlier. Sorry. Okay. Questions? Okay. Let me just write. The colleagues are also connected online. Let me just write their names. Okay. Okay, so going further, during the break, I have opened the Wikipedia web page for the HDMI standard. Okay, and this table shows different versions of this HDMI standard, and the newest version is this 2.1 from 2017. And you can see what is the maximum transmission bit rate in gigabits per second, depending on the version of this HDMI standard. This is the actual useful rate, data rate. This is the transmission rate because it has this kind of special coding. So how to 8-bit coding. Without going into details, this is the useful rate. Okay, this is the useful rate, 42.6 gigabits per second. Okay, for the newest standard, and for the first standard it was 3.96. It was this value that was capable of transmitting full HD quality video with 10 bits value for each RGB value sample. Okay, and all of this 48 gigabits raw or 42.6 gigabits useful data rate is achieved with only 3 data lanes, 3 twisted pair lines. And it is shown here. So you have this data 2 plus minus with shield, data 1 plus minus with shield, and data 0. And finally clock with shield. So you have 1 twisted pair for the clock, 1 and 3 twisted pair lines for data, 1, 2, and 3. Okay, and that is each of such lanes transmit 1/3 of the aggregate total rate. So this 48 gigabits is divided over 3. So over each individual lane, it is 16 gigabits per second. Okay, over individual data lane. And that is the fastest serial standard that exists, because this twisted pair for the Ethernet is 10 gigabits for 1 twisted pair, and this here is 16 gigabits raw data for 1 lane. Okay, so just to get the idea, what are nowadays data rates that you have for media signals. So the raw data rate is really immense, enormous. And of course, if you want to store this, you cannot store it in this raw format. Otherwise, your hard disk would be full in a few minutes. So if I would have such fast hard disk to be able to write this 46 gigabits per second on a hard disk, of course I cannot write this with such a high speed, even with the fastest flash drives. I would fill up this drive in a few minutes and that would be done. So obviously, to transmit such data, high quality data, you must compress it quite a lot. And the idea of these multimedia systems and technologies is how to compress this raw data video signal in a way that is indistinguishable from the original version, from the raw data version, but of much lower data rate, several orders of magnitude, 2 orders of, so 100 times lower rate than it is used for the connection between your PC monitor and your PC. Okay, and that is the. So it is also discussed here. So for example, you have this Blu-ray disc. It was some technology that existed in 2008. It is completely obsolete nowadays. So it was used to store video content, so not on DVD, but on this Blu-ray disc. Capacity was 50 gigabytes. It had 2 layers and 2 sides. And if you would write this full HD signal without any compression to such Blu-ray disc, it will last only 2 minutes and 30 seconds. Okay, and this would be full. So without any compression, 2 minutes and 30 seconds was the capacity of the disk. And of course, the required rate that you needed, this 3-point-something gigabits, was not achievable with the actual hardware. It could only achieve maybe 260 megabits per second, the highest possible write speed, what was much lower than the required 3 gigabits per second. So obviously, you cannot store it, so you are limited with the highest write speed, you are limited with the capacity. Okay? And that is the reason why we need to compress it. Okay? That is a summary of what we have covered so far. And I will now go to the next presentation. We will maybe cover only first part of this next presentation. And that is introduction to compression, or to entropy coding, so-called entropy coding. Sorry, I have to find it. I have it here. I have it here. Downloads, MT02 presentation. Okay, coding of media signals. So the title is Coding of Media Signals. Obviously, as we saw, manipulation of digital media content in the nominal or raw resolution is not possible. Such format is obviously not useful. It has too high data rate, while the actual information content is much lower, several times lower, or maybe tens or several hundreds times lower than the actual data raw rate is for the media signal. So obviously we have to separate what is important from that part of the media signal that is predictable, that is somehow redundant. So we have to separate something that is really necessary, innovative, from something that is redundant. And generally, this is done by coding. And this English term coding is, the meaning of the word is representing information using sequence of bits. And compression is only one aspect of coding. So data compression is one possible way of coding information, where I want to compress the information. I take the input data and I have the output rate that is lower than the input rate, while still maintaining the full quality, the full information that came in, if I have this lossless information coding. If it is lossy coding, then I introduce the error, I achieve the compression, okay, but I don't have the ideal reconstruction if it is lossy coding. So normally, the system is, you have raw data input, media signal, it is passed through the encoder, it does this compression, then it is forwarded over the network, or it is stored on some media, and the decoder does the inverse, it decompresses this media, and I get the output that is, again, this raw data format, but it can be the same as the input, or it can be approximately the same as the input signal, and that depends on the type of the encoder and decoder, whether this encoder and decoder were lossy or lossless. Okay, in the context of compression, this procedure is also called redundancy removal, because I want to remove the redundant part of the signal from this innovative part of the signal. And the task of compression is that based on this raw media format, I want to transform this data sequence into equivalent digital representation that is shorter, smaller, of lower rate, where I have reduced or completely eliminated the redundancy. So this redundancy in the signal is either reduced or completely eliminated. And that is the task of compression. In the wider aspect, in the wider definition, this coding can be divided into three subgroups.
First group is so-called source coding, and we will be covering this topic more or less mostly in our course. So this source coding aspect. Second aspect is the entropy coding. We will also cover this in the context of compression. And the last aspect of coding is so-called channel coding. It is also sometimes called redundancy coding, or either for redundancy check or for error correction. So these are the so-called error correction codes, or codes for verification whether the message was transmitted correctly. So error detection codes, let's say. Okay, and all of this is the called channel coding. So normally, a typical example of channel coding is this CRC code, cyclic redundancy check. So besides transmitting the data buffer, you compute this cyclic redundancy value for this data block, and transmit this CRC value together with the data block. On the receiving end, you get this received block, and then you compute in the same way this CRC value from the received values, and compare the computed CRC value with the received CRC value. And if they're the same, then you conclude, okay, this block was transmitted without any errors. So the CRC is maintained the same that was transmitted, it was computed at the receiving end. And that is part of the channel coding. The other aspect of channel coding is adding redundancy to the signal. Why? Because you have random bit errors during transmission. Let's say, in average, 100 bits are randomly toggled to other value. And you have some garbage on the receiving end, because each 100 bits approximately is of wrong value. And then you want to correct this random bit error. And to be able to correct this value, you must add redundancy information to the transmitted signal. And based on this redundant information, you can still correct the received information, because you have, let's say, just the simplest way to illustrate, let's say that you send 2 replicas of the same data block, okay? And then if I have 2 replicas, I can easily find whether the content is the same in each of these repetitions. And I can easily find which bits are wrong, which bits are changed. Then maybe I can require the retransmission of this part of the message that was wrongly received, and so on. So there are different tricks how you can use this redundancy information to correct the received information. So all of this is part of the channel coding, and we will not be covering this topic in the course. We will be concentrating on the source coding and on the entropy coding. Because both of those two, they are reducing the rate, while this last one is increasing the rate to increase the reliability of transmission, to have higher accuracy of the received signal. Okay, then we said this, and I already told you, so there are 2 versions of this encoding and decoding. So it can be either lossless, in a way that exactly the same sequence is restored at the receiving end after decoding, exactly the same data sequence as it was at the input of the encoder, and that is lossless coding. And alternative is lossy coding, and in this case, the output is approximately equal to the input signal. They are similar, they are not equal. They are only approximately equal, but they are approximately equal in the consistently with our perception. Okay, so the error is either not visible, the error is not hearable. Okay, we cannot hear the error, the difference between the original signal and the reconstructed signal, because it takes into account our psychoacoustic perception of the signal or visual perception of image or video sequence. Okay? And so these are these lossy coding standards. Okay? And this ideal reconstruction in the lossless is only possible if I really keep all of the information intact. So I only reduce the rate, but I use the coder and decoder that can reconstruct ideally the original sequence. Okay. So what is the difference between source coding and entropy coding? The basic difference is that source coding knows what the source is. That is the reason why it is called source coding. So if the source is sampled speech signal, it has certain properties that can be utilized in compression. If the source is audio signal, music or whatever, then again it has certain properties. It can be utilized in compression to achieve the best possible compression ratio for this kind of signal. In both cases, I know what the source is, and I adapt the coder and decoder to the properties of the source. Okay? On the other hand, the entropy coding simply attacks or processes this input sequence as a just bunch of data, bunch of values, and tries to remove the redundancy based on statistical properties of this digital data sequence. And just to be most figurative, it is this zip that you use on your PC or RAR that you use on PC. Why? It has any input. So the input can be any file. And it just computes the statistics of each possible data value in this file and uses some entropy coding techniques to reduce the rate for representation of your input file. At the end, after unzipping or using this RAR, then you get the original file without any loss of information. So you don't have the information what was in the file, whether the file was image or the file was Word file from your word processor or Excel file. It doesn't matter. It simply attacks this information as a bunch of digital data values. Okay? On the other hand, the source coder exactly knows what the input is. Okay? And that brings us to the next topic, and this next topic is information and entropy. And this information and entropy will discuss especially this part of entropy coding. So how to achieve data compression using entropy coding. Okay, information and entropy. In the preparation of this material, one doctoral student, Ivan Dokmanic, was also helping us. And Ivan is now a very distinguished professor in Basel. He was first in US on some, or he finished his PhD in EPFL, Lausanne, so in Switzerland. Then after his PhD, he was first working in USA, this Urbana-Champaign in USA, University of Urbana-Champaign. And after that, he moved to Europe, to Basel, and now he's in Basel as a professor. He recently got this ERC grant from European Union, and that is very nice thing because you can employ a lot of doctoral students from this ERC grant money. Okay? And Ivan at that time was a doctoral student here, and he helped us prepare these materials. Okay, so what is the information? How can we define information or the information quantity? And we can define it as a level of surprise for some event. Okay, level of surprise for something happening. So something happened. So if we were very much surprised, then the information was very high. If we were not that much surprised, then the information is not that high. Okay, so that is the simplest way how we can define the quantity of information. So, for example, assume that you want to guess what is the female first name, the first name of a girl. And then somebody tells you that the first letter of the first name is letter M. And this letter M is a quite common first letter for the first name, for the lady's name. And of course, with this information, he has not given up you a lot, because there are many female names that are starting with M. I don't know how many, 50 maybe, something like that. So there are 50 different personal names, first names, that start with M. But if the same person tells you that the first letter of this first name is this Z in Croatian, is this fricative version of Z, so this Z, then the quantity of information is much higher, because there are only a few female names that start with Z. Maybe 3 or 4 female names, Željka, Žana, whatever. Maybe only a few names are starting with Z. So in that sense, the quantity of information is much higher if I say, okay, the first letter of the first name is Z. We can much easier guess which name it is. Okay? So assume that this memoryless source of information generates output from discrete symbols. So this here is a set of symbols. You can consider this as an alphabet. So these symbols are from alphabet A, B, C, blah, blah, blah. We have a set of symbols, and this alphabet defines all possible symbols that the system can generate. And now I have to know what is the probability of generating each symbol from this dictionary. Okay? For example, you have computed the long-term statistics of textual information. You have taken all different textual sources in English, and you have computed what is the statistics of occurring letter A, B, C, blah, 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 all the letters of English alphabet. And then the probability of this letter is denoted with this pi. And of course, if the letter is more common, if the probability of this letter is higher, then the information it conveys is lower. So if it is, for example, letter A or some other vowel that is quite often in your text, then the information that it is carried with this vowel A or E or whatever is very low. And this quantity of information can be estimated as log 2 of 1 over pi. So log 2 of reciprocal probability of observing this symbol. And that was the reason why, if I said, okay, the letter Z is very uncommon, is very seldomly observed in Croatian alphabet, then this probability is some small value. I don't know, 1 in 1,000 or maybe even less than that is the probability of observing this letter Z. And then this 1 over 1,000 is 1,000, and then logarithm 2 of 1,000 is approximately 10 bits. Okay, logarithm base 2. So I compute logarithm base 2 of 1,000. If that would be 1,024, it would be exactly 10 bits. So the information that I need to encode this letter Z is around 10 bits. Because this is based on the statistics, how often do I observe this letter Z? If I have some common letter like A, E, U, so these vowels are quite common in Croatian text, and the probability might be maybe 1 over 10. So probability of observing a letter, okay, it's maybe too much, but let's say 1 over 20, okay, 1 over 20. In this case, this reciprocal value of probability is 20, and then taking logarithm base 2 is 4 times something bits, 4.5 bits in the case of letter A. So we see that depending on the probability, we have different information for each letter of the alphabet. Okay? And then, if I want to compute the entropy of such sorts, the entropy is like average measure of information. What is the entropy? Average measure of information of such sorts. I would simply average this value, but average using the probability of this symbol. So this J letter, I had in this case the information was 10 bits. But it happens only in 1 over 1,000 times. So to have the average information content, I multiply this value with the probability of this. So this is times pi. If I multiply this with pi, I would get the relative contribution of this letter to the total information content of this source. As for the letter A, this value was smaller, 4.5, but the probability of letter A was much higher, 1 over 20. So I have 1 over 20 times 4.5 bits. And then I simply add this for all letters of the alphabet. And I get this kind of equation. So I have probability multiplied by the information of this symbol. The information is logarithm 1 over pi, multiplied by the probability of this symbol, pi. And I add up all symbols from 1 to n. So for the whole alphabet, from A, B, C, blah, blah, up to the last letter, whatever, Z. Okay? And what I get is the average measure of information for this source. This average measure of information is called entropy in English. Entropy is the measure of information for some source, memoryless source. And memoryless source, this here, bezmemorijski izvor, memoryless source, it means that sequence of symbols that are generated are independent of each other. So if I generate letter A, the letter after that, it does not depend whether the previous letter was A, B, blah, blah, blah. So each letter that is generated independently of the letters before or after that particular symbol. And that means that the source is memoryless. So each output symbol is generated only based on the probability of observing this particular symbol. Okay. And of course, I can take this 1 over pi as a minus log pi, and I get the final expression for the entropy. And this is very well known, okay? Just sum up all the products of probability and multiply it by the logarithm of probability. So this logarithm is base 2 logarithm. Logarithm is base 2 logarithm if the final result is expressed in bits. So if I measure this information in bits, then this base of the logarithm is base 2. And the alternative to this is so-called natural logarithm, so base 2.7 blah blah blah. In this case, it is expressed not in bits but in nuts. Okay, these nuts are going logarithm base a of pi. Okay, then it is not in bits. No, it is in nuts. Okay, nuts. Okay, so this is ln. Okay, ln of pi. Okay, ln of pi. So this is then in nuts. Okay, if it is logarithm base 2, it is in bits. Just the terminology to be formal. Okay, and I guess so. The definition of the entropy that I used before, this definition, it corresponds to the lowest possible average bit rate needed for quantizing, for representing this source. Okay? So if I really have this sequence of letters, if this sequence of letters are generated with the probabilities P1, P2, P3, up to Pn, then the lowest possible average rate needed to quantize this, to represent these symbols, is what? Exactly this value. Exactly this value. Just before the break, before the end, let's make a very simple example. Let's assume that our alphabet has only 4 letters, A, B, C, D. A, B, C, D. And then the probability, Pi, here, 1/4 for each I. So we have equal probability of letters A, B, C, D. And we generate a sequence, okay, so A, C, D, B, B, A, blah, blah, C, D, blah, blah. In average, I would have 1/4 of A's, 1/4 of B's, 1/4 of C's, and 1/4 of D's in any long length of the sequence. And now I ask myself, what is the required, the lowest possible required rate to encode this sequence? Of course, we know the answer. The answer is 2 bits. You have 4 symbols, and they are equal probability. And of course, we expect that the result should be 4 bits. Can we verify this using this expression? Yes, we can. So this entropy H of S is then sum 1I 1 to 4 Pi log 2 Pi. And this Pi is equal to 1/4 for each I. So I have sum 1 to 4, 1/4 times, and this logarithm 2. So I have minus here. So negative sum. This logarithm Pi is -2. So this is 2 to the power of -2. Is this value, so logarithm of this is what? It's -2. Okay, so logarithm of 2 to the power of -2 is -2. Okay, and then we have this 1/2. Okay, so minus and minus are cancelled, plus and plus, and I have sum of 1/2 from 1 to 4. And of course, this is 2. And I have the information rate of 2 bits per sample, per symbol. Better to write it per symbol. So for each symbol, I need at least 2 bits to represent this symbol. And of course, we knew that answer, because if you use a binary code for these symbols A, B, C, D, and I encode this 0, 0, 0, 1, 1, 0, 1, 1, then the average rate is exactly 2 bits, because each symbol is coded with 2 bits. So it was a trivial example, okay? But now what we will consider on the next lecture is what if the probabilities are not the same? So what if probability of some symbol are much higher relatively to the other? Then in this case, obviously, this binary code is not the optimal solution. So I might have another solution that has a higher compression efficiency, so the lower average bit per symbol can be achieved if I use better entropy code. And ideally, in the ideal case, I would achieve this H of S. So this H of S is a bound, a lower bound. I cannot be better than that. That is the best I can get. So this entropy measures the lowest possible rate, bits per symbol, that I can achieve with entropy coding. Better the coder is, closer is to this bound. Okay, but it can never exceed this bound. It can never be better than this bound. So that the average rate is even lower than the entropy computed according to this expression. And that will be the topic of the next lecture. Okay? Questions? Okay. So then see you in 1 week time. Same time. Okay. Bye-bye.
Bye. Thank you.
Bye bye, see you next time.